Have you ever heard about using finite element analysis in vertebrates? Yes, it is possible to use a tool from mechanical engineering to study the biomechanics of living and fossil vertebrates. It allows you to study locomotion or chewing and understand the evolution within their families. But what is finite element analysis, or FEA, which are the acronym of finite element analysis? Is the mathematical way to solve problems of elasticity in complex geometries. So you can divide the geometry in tiny elements, but in a finite number, where the equations are easy to solve. Then you can apply external forces in your model and understand how it deforms or how the inner forces are distributed inside the model. This method has been widely used in paleontology, anthropology, and functional morphology in general, because now we can easily digitize the bony structures so we can apply FEA in real geometries. But we cannot omit that so Anderson et al. Wrote in 2012 this sentence that today is still true. By definition and in practice, models are not literal representations of reality, but provide simplifications or substitutes of the events, scenarios, or behaviors that are being studied or predicted. All models make assumptions. Therefore, we are creating models that maybe are not enough close to the reality, but they can be very useful for our purpose. Following the idea of simplification that Anderson was underlying, I want to show you that there are different kinds of elements that we can use when we are creating a FEA model. The use of some of these elements imply, of course, a simplification of the reality to a simple model. So, let me introduce you these different kinds of elements and their features. First of all, the element beam. You use them when your geometry is aligned and you are working in the 3D space or in 2D. You define them creating the mesh of the elements in this line and defining a cross-section. You can see an example of their use in Anderson et al. 2007, where they simplified the skull of a fish in a linkage of 4 beams. Second, the element shell. You use them when your geometry is a surface and you are working in the 3D space. You define them, creating the mesh of the element in this surface and defining a constant thickness. You can see an example of their use in my works about carpal bones because they have a tiny layer of cortical bone with cancellous bone inside. Third, the plane elements. You use them when your geometry can be simplified to a surface that can lie in a 2D plane. Be careful, because these elements are not 2D elements. They are called plane elements because they use the equations of plane elasticity. The surface is lying in a plane. The forces you apply should lie in this plane and you must define a thickness. The thickness plays a role in the results, so you cannot avoid it, and for this reason you cannot use the term 2D here. You can see an example of their use in models of mandibles. For example, I use them to create FEA models of the mandible of several primates. Which are the differences between shell elements and plane elements? Shell elements are not lying in a plane, or if yes, they allow forces that are not in the plane, like perpendicular forces. You can see this difference in the FEA models of the skull of several temnospondyls, where the forces I applied are perpendicular to the flat surface of the skull. And finally, solid elements. You use them when your geometry is a volume and you are working in the 3D space. They are the most spread and the ones people is always using when you have a real geometry from a CT scan, photogrammetry, or laser. You can see an example of their use in this work of Jack Zheng, where he modeled the mandibles of different carnivora in 3D instead of other more simplified options. These are the options you have for adapting your geometries to your FEA model. Maybe you think that if you have a CT scan and you create a FEA model with solid elements, then you have a very realistic model. I regret to inform you that this is the first step when creating FEA models, and there is still a lot of decisions to make. And probably, in most of them, you will need to simplify your model, because always remember that models are not literal representations of reality.